The incredible journey of Voyager, humanity's greatest space adventure. In the vast expanse of space, two remarkable machines continue their eternal journey into the unknown. The Voyager spacecraft, launched in 1977, represents humanity's most ambitious attempt to explore the outer reaches of our solar system and beyond. Today, we'll delve into their extraordinary story, from their groundbreaking discoveries to the ingenious technology that made their mission possible. Our story begins in the mid-1960s, when a young NASA engineer named Gary Flandreau made a fascinating discovery that would change the course of space exploration. Flandreau identified a rare alignment of the outer planets that occurs only once every 176 years. This celestial choreography would create a unique opportunity to visit multiple outer planets using a technique called gravity assist, essentially creating a cosmic highway through space. This revelation led to what would become known as the Grand Tour mission, an ambitious plan to explore Jupiter, Saturn, Uranus, and Neptune in a single journey. The challenge of building a spacecraft capable of surviving such an epic journey was unprecedented. Remember, this was the 1970s, an era when the computing power we now carry in our smartphones was the stuff of science fiction. The engineers at NASA's Jet Propulsion Laboratory had to develop solutions to problems that had never been encountered before. They created spacecraft that would need to operate flawlessly for decades, far beyond the reach of the sun's warming rays. At the heart of each Voyager spacecraft lies its power source, the radioisotope thermoelectric generator, RTG. These ingenious devices convert heat from naturally decaying plutonium into electricity, providing reliable power even in the coldest reaches of space. Each Voyager carries 3 RTGs, which have been faithfully powering the spacecraft's systems for over 4 decades. This innovative solution to the power problem was crucial, as traditional solar panels would be useless in the dim light of the outer solar system. The spacecraft's computer systems were equally revolutionary for their time. Each Voyager carries 3 interconnected computers: the Computer Command System, CCS, controlling the spacecraft, the Flight Data System, FDS, managing the instruments, and the Attitude and Articulation Control System, AACS, maintaining orientation. These computers, with just 69.63 kilobytes of memory each, less than a single modern digital photo, have processed and transmitted millions of measurements and thousands of images across the vast expanse of space. The scientific payload of each Voyager is a testament to human ingenuity. 11 instruments work in concert to study everything from magnetic fields to cosmic rays, from plasma waves to planetary atmospheres. The imaging science system, the spacecraft's eyes, has captured some of the most iconic photographs in the history of space exploration. The cosmic ray system detects high-energy particles, while the magnetometer measures magnetic fields. The plasma science instrument studies the solar wind, and the radio science system analyses atmospheric composition. Together, these instruments have revolutionized our understanding of the solar system. In the summer of 1977, humanity embarked on its greatest journey of exploration. Voyager 2 launched first, on August 20th, followed by Voyager 1 on September 5th. Despite launching second, Voyager 1 was placed on a faster trajectory. Each spacecraft carried enough fuel for about 100 small course corrections and a few major ones, a necessity for the precise navigation required to visit multiple planets using gravity assists. The Voyager's first major destination was Jupiter, reached in 1979. What they found there revolutionized our understanding of the giant planet and its moons. They discovered active volcanoes on Io, the first time volcanic activity had been observed beyond Earth. This discovery, made by navigation engineer Linda Morabito when she spotted a strange plume above Io's surface in a Voyager 1 image, opened up new possibilities about geological activity in the outer solar system. The The spacecraft revealed Jupiter's intricate ring structure, the complex dynamics of the Great Red Spot, lightning in the Jovian atmosphere, and two previously unknown moons. They also measured a magnetic field far stronger than anyone had expected. The encounters with Europa proved equally fascinating. The Voyagers gave us our first detailed look at its cracked surface, leading scientists to hypothesize about a subsurface ocean, a theory later confirmed by subsequent missions. This discovery would later influence our understanding of where life might exist in the solar system. Saturn and its magnificent rings came next, in 1980 and 1981. The Voyagers transformed our understanding of the ringed planet, revealing thousands of individual ringlets, mysterious spokes, shepherd moons controlling ring structure, and braided rings with unexplained kinks. The discovery of the F-ring, shepherded by two small moons, demonstrated the complex gravitational ballet occurring within Saturn's ring system. The close pass by Titan, Saturn's largest moon, revealed its thick, nitrogen-rich atmosphere. This discovery would later inspire the Cassini-Huygens mission, which found lakes of liquid methane on Titan's surface. The Voyagers also studied Saturn's other moons, discovering several new ones and revealing the unique characteristics of the known satellites. Enceladus's remarkably reflective surface, Mimas's enormous impact crater, making it look remarkably like the Death Star, the bizarre terrain of Iapetus, and the sponge-like surface of Hyperion. In 1986, Voyager 2 achieved another historic first by visiting Uranus. This encounter was particularly challenging due to Uranus's unique orientation. The planet essentially rotates on its side. The spacecraft discovered a magnetic field tilted 60 degrees from the planet's rotation axis, 10 new moons, and a new system of rings. Despite receiving minimal solar energy, Uranus showed complex atmospheric dynamics and an extremely cold temperature of 224 degrees Celsius. Perhaps the most surprising discovery at Uranus was Miranda, a small moon with one of the most diverse and bizarre surfaces ever seen. Its jumbled terrain suggests a history of being broken apart and reassembled multiple times, hinting at the violent past of our solar system. Neptune, reached in 1989, marked Voyager 2's final planetary encounter. Despite its great distance from the Sun, Neptune displayed surprisingly dynamic weather patterns, including the Great Dark Spot, a storm system similar to Jupiter's Great Red Spot, and the fastest winds measured in the solar system, reaching speeds of 2,100 kilometers per hour. The spacecraft also discovered a system of rings with unusual clumps called ring arcs. Neptune's largest moon, Triton, proved to be one of the most fascinating objects in the solar system. Voyager 2 observed nitrogen geysers erupting from its surface and measured the coldest temperature of any natural body in the solar system at 235 degrees C. Triton's retrograde orbit suggests it's a captured Kuiper Belt object, providing insights into the early solar system's formation. Each Voyager carries a remarkable addition: the Golden Record, a time capsule containing sounds and images from Earth. This includes 115 images, natural sounds like winds and animal calls, musical selections from different cultures, and greetings in 55 languages. Made of gold-plated copper, these records should last for hundreds of millions of years, carrying a message from humanity to the stars. The communication system of each Voyager is a triumph of engineering. Using just a 23-watt transmitter, about the power of a refrigerator light bulb, the spacecraft can send signals across billions of kilometers that are detected by NASA's Deep Space Network. The system uses a 3.7-meter high-gain antenna, X-band radio frequency, and sophisticated error correction coding. Today, it takes over 21 hours for a signal to reach Voyager 1 from Earth. After completing their planetary missions, the Voyagers began exploring the outer reaches of our solar system. In 1990, Voyager 1 captured one of the most profound photos in human history. The pale blue dot image, showing Earth as a tiny point of light from 6 billion kilometers away. As Carl Sagan eloquently noted, this image showed us our place in the cosmos. That's here, that's home, that's us. The Voyagers have now entered interstellar space, becoming the first human-made objects to leave our solar system. They cross the termination shock, where the solar wind slows dramatically, in 2004 and 2007, and then traverse the Helios Heath, a turbulent region where the solar wind is compressed. Voyager 1 entered interstellar space in 2012, followed by Voyager 2 in 2018. Even today, the spacecraft continue to make discoveries, measuring the density of interstellar space, detecting previously unknown phenomena, and studying cosmic rays beyond the solar system. They've detected interstellar plasma oscillations and are helping us understand the boundary between our solar system and interstellar space. As the Voyagers age, engineers face increasing challenges. The RTG's power output decreases by about 4 watts per year, requiring constant prioritization of which instruments to keep active. Both spacecraft have experienced memory problems, but engineers have developed creative workarounds using redundant systems. Despite these challenges, software updates are still possible across the vast distances. The Voyagers will continue operating until around 2025, when their power will become too low to run any instruments. But their journey won't end there. Voyager 1 will pass within 1.6 light-years of star AC +79. 38888 in about 40,000 years, while Voyager 2 will pass within 1.7 light-years of star Ross 248 in a similar time frame. The scientific impact of the Voyager missions is staggering, with over 5,000 scientific papers published and countless discoveries that rewrote textbooks. The missions have revolutionized our understanding of planetary formation and solar system evolution. But perhaps more importantly, they represent humanity at its best, curious, ambitious, and determined to understand our place in the cosmos. Even today, a dedicated team of engineers and scientists works to keep the Voyagers operating, squeezing every possible bit of data from these remarkable machines. As they continue their eternal journey through the Milky Way, they carry not just scientific instruments, but also humanity's message of peace and friendship to the stars. The Voyager missions demonstrate that with vision, dedication, and ingenuity, we can achieve things that seem impossible. They remind us that exploration and discovery are fundamental human traits, driving us to push beyond known boundaries and venture into the unknown. Technical details for reference. As of 2024, Voyager 1 is approximately 24 billion kilometers from Earth, traveling at about 17 kilometers per second, while Voyager 2 is about 20 billion kilometers away, moving at roughly 15 kilometers per second. Their original power output of 470 watts has decreased to about 249 watts. They now transmit data at about 160 bits per second and have returned over 7 trillion bits of data and more than 67,000 images. The mission's total cost, including 47 years of operations, is approximately $975 million.